Hello, my name is André. I'm here to present our work called Attention Modules Improve Image Level Anomaly Detection for Industrial Inspection, a DifferNet case study. This work was done in cooperation with three universities, Universidade Federal de Pernambuco, Universidade Federal Rural de Pernambuco, and the Technical University of Chemnitz. So when considering industrial inspection in control scenarios, we had the advent of the MVTec Anomaly detection dataset in the past few years, which fomented many new classes of anomaly detection models. A popular approach to deal with this dataset is to use feature embedding extraction for unsupervised anomaly detection. Two ways to benefit from these feature embeddings are using distribution maps or normalizing flows, or memory bank of patches. So as we can see in the methods listed below, they mainly overcome all of the challenges imposed by the MVTec anomaly detection dataset. However, we have many other challenges in the industrial inspection scene. So for example, the challenges of industrial inspection in the wild are many. For example, images from those kind of inspection vary on illumination, angulation, orientation, background, resolution, defect size, and many other characteristics. Of course, the defects in industrial inspection in the wild also are unpredictable. We don't have many data. Mainly data regarding defective objects. Take for instance power line inspections, as you can see in the video. We have corrosion as our main defect problem, missing insulator caps, and many unpredictable defects such as bird nests and stuck kites in the power lines. The main hypothesis of this work is that attention modules can improve the accuracy in the wild scenarios. But how we can choose the best model to add those attention modules? We noticed that the DifferNet method achieved the best out-of-the-box results in the InsPLAD-fault, which is a power line inspection dataset. So to be considered a successful hypothesis, the attention usage in unsupervised anomaly detection should not present deteriorated performance on inspection in controlled scenarios. In other words, we want that the attention models improve in the wild scenarios, but we don't want that it deteriorates in controlled scenarios. For that, we propose the AttentDifferNet, which strategically combines the DifferNet method with attention modules by placing those attention blocks during the feature extraction step of the anomaly detection method. One block for each step of the process, the beginning, in the middle, and in the end of the feature extraction step. So this is a very important thing to do, because in this part the network will extract the most important features in the image. So, as we previously said, coupling modular attention mechanisms to anomaly detection modules should help the model to focus on what is important. For that, we chose two attention modules. One is the squeeze and excitation networks, and the other is the convolutional block attention modules, which are quite popular attention modules and very easy to integrate. The datasets used for our analysis are three. The main one is the InsPLAD-fault dataset, which is the in the wild dataset, more focused on the power line inspection. And the two other datasets are controlled scenario datasets, which is the MVTec AD and the Semiconductor Wafer dataset. So let's go to our quantitative results. And we can see here in the second row that our AttentDifferNet variation with the squeeze and excitation networks is able to achieve the best overall area under ROC in all categories and in overall as well. Just to point out the highlights here, the bold font indicates the best category results overall methods, and the underlying values show the best result between the three DifferNet variations in the first three columns. So the first part of our hypothesis is confirmed that attention modules do help the anomaly detection method, more specifically the DifferNet method, to focus on what is more important in terms of quantitative metrics. So considering the controlled scenario datasets, we see that the AttentDifferNet is not only able to not deteriorate from the standard DifferNet, but is also able to improve the standard DifferNet results in all categories. Clearly, it is not capable to get the best results overall, all the methods analyzed, but the second part of our hypothesis is also confirmed here, at least in this data set. And in the third data set as well, we see that the performance is improved regarding the standard DifferNet. So the attention models do improve the performance quantitatively in the wild, and they do not get in the way of the method on controlled scenarios, being able to even improve the performance on those scenarios as well. For the qualitative analysis, we see here images from two data sets. We use the GradCam tool to extract the gradient activation maps. So the second row, the DifferNet row here, we see the gradient activation maps of the model in the last layers of the model. So we can see that the DifferNet, the features extraction step is a bit confusing. It's not able to focus very well on the objects of interest, and also in the second data set, MVTec, it has some confusion. And in the third row here, we see that our proposed method, AttentDifferNet, is able to focus on every object of every class. In this case of in the wild data set, and in the case of the controlled scenario dataset MVTec AD, it's also able to focus on the anomaly itself, not only the object, which is quite interesting. Just repeating myself, it's important to note that we don't use any pixel level annotation in this work, only image level labels. So finally, this work proposes the AttentDifferNet, which is an attention-based DifferNet. It is qualitatively and quantitatively superior to the standard DifferNet in all classes of the three image level anomaly detection datasets, which are from multiple domains in the wild and controlled scenarios. So AttentDifferNet achieves the state-of-the-art performance on InsPLAD-fault, which is a dataset for power line inspection in the wild, which is quite relevant for the problem in question. And finally, confirming our hypothesis, the usage of attention models do improve unsupervised anomaly detection in all three tested datasets, one in the wild and two in controlled scenarios, on an average of 1.77 percentage points. So that's it. Thank you very much.